take it away.
Okay, thanks, Kat. Yes, so we're changing back in scale to the larger scale and to the broad Southern Ocean, and I'm going to give a talk which is not a lot of current research. There'll be some current research at the end, but I want to give a talk which is maybe a little bit more of a review of what we know about eddies and their importance in the Southern Ocean. And to do this, I need to first explain a couple of things about my worldview of eddies and the ocean and a framework to think about them. And so I'm doing that with the benefit of this movie here. And for those who are watching on Zoom, this won't work very well for you, but sorry about that. And this is a segment of a movie where we've gone to the mid part of the Southern Ocean, and we're looking through the full depth of the ocean, and we're looking at layers of density and layering them on top of each other. And so this is the way I think about the ocean, and particularly the Southern Ocean, is that it's really a series of stacked shallow water models. Yes, there's diaphycnal mixing in between them, there's bottom water formation, there's things like that. But a lot of the dynamics can be explained by an understanding of these stacked shallow water models. And I'm just going to, if I can go back and start this again. And what I'm showing here is these isopycnals, and on these dividing isopycnals, I'm showing velocity in the colour. And what you can see is where these isopycnals go up and down, well, that's where the eddies are, and these eddies are quite deep reaching. In this part of the ocean, they're extremely dynamic. They're moving around all over the place, and you can see that really the gradients in this. What you could see is that the gradients in these isopycnal surfaces are where there's high velocities. Okay, and so when you think about hard, that's all pretty natural, but what I guess I want to get across the point that on these isopycnal surfaces, it's very easy for things to move laterally, and it's relatively harder for things to move across as in the diaphycnal direction. So that's the first thing. And the second thing is that there's interactions between these layers, and we're going to talk a little bit more about that. Now, if all these turbulent processes that we saw going on in the ocean in that animation, if all these turbulent, I think it is animations, by the way, break it. Seems to happen every time. If all these turbulent eddies that are occurring on these isopycnals, if they just have if they're just moving things around and back in the same place, then obviously don't have enough net, right? So the big question is what net effect do the eddies have on the circulation and on the transport of traces and mixing and so on and so forth.
You need another slide.
Yeah, do you want to change the slide?
It could be. You never know. Just try doing that. No?
Yeah.
No?
Yeah, I've been doing that. This is the fourth go. It keeps actually coming much.
No, that's useful. Just after I finish.
Yeah, sorry.
So I was at a conference once. I can use the break to tell you a story that I've been thinking about this morning. I was at a conference once, and it was in Prague, and the audio visual was terrible, almost as bad as the ANU. And Jan Zika stood up to give a talk, and the whole system just went down, and they couldn't get it back up and running. And Jan just said, "That's fine. I can give my talk anyway." And he gave his entire talk just waving his hands and, things like that. So it is possible to give your talk without slides, but only for special people. Okay, so what's the net effect of all these ocean eddies? In other words, why do we really care? And do they affect the large scale, or are they just shifting things back and forth on a small scale? And of course, I'm going to argue that we do care, but I want to delineate three different things that eddies do which I view as being disparate and different effects of eddies. And these different effects are often lost in the wash. The first is that eddies act to stir traces along isopycnals. And Helen mentioned this a little bit this morning. The second effect is that eddies actually transport momentum, and they transport momentum, well, they transport momentum laterally, but they particularly in the Southern Ocean transport momentum vertically, and that turns out to be really important. And eddies also transport mass or volume. So, and here I'm talking about volume transport or thickness fluxes along isopycnal layers. So I'm going to talk about that a bit. And so if you believe me that all the above are effects of eddies, then what do we know about the dynamics controlling the eddy field, and what have we learnt recently? And so this scale is really an outline of my talk, and I'm going to get to this bit at the end. And I should add, Kat, can you give me like a 5-minute warning, because I've completely lost track of time. So I'm trusting you to tell me when I should finish up. Okay. So we did hear about this morning. I'm going to start out by talking a little bit about isopycnal mixing. So we heard about this in Helen's talk. And really the argument here is that along an isopycnal, eddies and other processes can move things about very rapidly. And when they move things about very rapidly, then you get this filamentation that you can see here. This is from Adele's review paper on ventilation. And it turns out that, that you can actually get very high lateral transport of traces. And by lateral, I mean on an isopycnal. In the Southern Ocean, these isopycnals are sloping up to the surface. So this is a way to get traces down into the ocean. And that can happen for traces like heat and salt that we care about because of their dynamical effects, or oxygen or carbon dioxide or other traces that are passive within the ocean, but are needed for various things. So just to give you a feel for how much we know about this isopycnal stirring and how big it is, I've stolen an image showed Grothkamp's paper from a couple of years ago, where they tried to do a calculation of just how big the diffusivity due to eddies along isopycnals are. And this, I think, is probably a similar calculation to the Sylvia Cole paper that Helen showed earlier. What you're seeing on the left is, this is the mesoscale eddy diffusivity at the surface, and this is a transect through the Atlantic Ocean on this really, really thin dashed grey line, showing the vertical structure of the mesoscale eddy diffusivity. And you can see here that, firstly, the absolute value of these is quite often, up to 1,000 metres squared per second. And 1,000 metres squared per second, I mean, what's that, 10 to the 9 times molecular? So it's pretty massive, whatever this isopycnal stirring is doing. The way this is calculated is through a recipe which includes both the URMS, or if you like, the square root of the Eddy Kinetic Energy, and a mixing length, along with a suppression factor where the mean flow is meant to slow down these this lateral stirring. My personal view on this sort of an estimation is I actually don't know how good it is. I'm not sure there's a really good way to test how good it is. But if we take it even with a grain of salt, then the point is that this whole prescription is proportional to URMS. So in effect, the more eddies, the stronger the eddy field, the larger the eddy kinetic energy, then you should have greater mesoscale eddy diffusivity. So you could argue that the strength of the eddy field controls this mesoscale eddy diffusivity, subject to the other things that are going on in that equation. Okay, so that's the first thing about eddies, and I think oceanographers are generally fairly familiar with that idea. Oceanographers may be less familiar, sorry that my headline is gone there. less familiar with the effects of momentum transport from eddies, and I want to take a little bit of time to explain that today. We'll see how far we get. So what I'm drawing in this little schematic here on the left is this purple line here is some isopycnal somewhere in the Southern Ocean. And this, you can see there's sort of a bump in it. And let's just imagine for argument's sake, that on one side of this bump, there's high pressure, and on the other side of this bump, there's slightly lower pressure, okay? Then you can imagine that if you sum up all the forces on this sloping isopycnal, that is, you times the pressure by the derivative of this, the spatial derivative of this interface height, then there's a net force being exerted on this interface. In other words, there's a transfer of momentum from this upper layer above the interface to the layer below the interface. So that is how something that is called interfacial form stress works. Form stress also operates at the bottom of the ocean, where exactly the same thing can happen on topography. But the bottom form stress that you're talking about there is something that can happen with a mean flow, whereas it would appear that by and large, you need some eddying flow to produce this, or at least if you have an eddying flow, then there'll be many more of these bumps upon which form stress can act to transfer momentum in the vertical, okay? And so this interfacial form stress is the main way momentum gets down into the Southern Ocean. And on the right-hand side, I've kind of framed our conceptual view of how momentum works on the zonal velocity. So this is a section now looking across the Southern Ocean, and these red lines here are isopycnals. And at the top, we have an input of momentum from the wind stress, and the eddy field helps to transfer that momentum down vertically. In the net, we understand that once we average around the Southern Ocean and average a little bit in the horizontal, in the net, this momentum is coming in at the surface and it's being lost at the bottom. And a lot of people explain this as a sort of a progressive stepping down of momentum as you transfer this momentum within the water column. But that's actually not strictly accurate. And in fact, just as important as the downward influence of this zonal momentum from the surface is the upward influence of the interaction with the bottom, okay? And so, for example, topographic steering will change the flow, and that will propagate upwards. And in fact, if you start with, we showed a number of years ago, if you start with flat isopycnals and you start blowing a wind, you actually have positive momentum coming in from the top and negative momentum coming in from the bottom very rapidly. And these meet in the middle, and ultimately they equilibrate. And I would add that this can also happen through standing meanders. So we shouldn't think of all mesoscale effects as just being due to the time-dependent eddy field. I'm going to step on to my next point in a moment, and then I'll come back to the momentum effect in a moment. But if this explanation of momentum and form stress doesn't make sense to you, please feel free to interrupt and slow me down. So the third thing that eddies can do in the Southern Ocean is they can help transport mass or volume along isopycnal layers. And that's what I'm showing in this schematic here on the left. And this is fairly easy to characterize. You can imagine that if you have variations in the thickness of this layer, H, and you have variations in the meridional velocity at a given time, then the correlation between those variations will produce a residual flux along this isopycnal. And I've, of course, exaggerated the effect here. But once again, this is something that we traditionally think of as an effect of eddies. Maybe one way you can think about this in quite an intuitive way is that if, let's imagine the Southern Ocean was a two-layer system and we just had a single sloping isopycnal, then baroclinic instability acting on, if this isopycnal has a thermal shear, a wind shear, which produces a baroclinic instability, then that baroclinic instability will tend to flatten that isopycnal, and that will move mass in this upper layer towards the south. So you can think of this thickness flux as being partly due to the APE release. When we look at the whole Southern Ocean, again, I'm looking at a transect here, and we understand from a bunch of recent studies that there is this residual mass flux in this direction as the isopycnals tilt up towards the surface. There's an eddy flux which brings fluid up towards the surface, and that's balanced by the ageostrophic Ekman transport in the surface layer. So when it comes to the effect of eddies on this thickness flux, I think there's a general assumption that the more eddies you have, the more eddy transport that you will have. And a lot of people call these eddy-driven flows because they argue that it's the eddies that are driving this residual flux up there. And I actually don't really buy the argument that these are eddy-driven flows. I actually think it's much more accurate to characterise this effect as due to the APE release of baroclinic instability. So one of the studies I want to touch on briefly is something that Alice Bartel did when she was here. This was the last paper of her PhD, and because life got busy, it's only just been published, but it was first submitted about 4 years ago, so it's been a little while. So this is a really simple case. It is a two-layer version of the ocean, and what I want to show you is we start out with a jet which is stable, and that jet goes unstable and it creates eddy kinetic energy, and this red line shows the eddy kinetic energy as you go along the domain, okay? And this cyan line here shows the cumulative southward transport. And so what this is saying is that as the eddies are growing, so when this cyan line has a slope, that's where the southward transport is, okay? So as these eddies are growing, that's where you have the southward transport. And so in other words, you don't get the maximum southward transport where the eddies are strongest, you get the maximum southward transport where the eddies are growing. And if you actually think about it for a little bit, you'll see, well, that's sort of obvious because these eddies are formed by the release of APE. But there's a lot of parameterizations that want to parameterize the eddy thickness fluxes as proportional to the eddy kinetic energy, which I don't think is true. There's a particular case in which it's really not true, and that is this case here, where you have a lot of southwards flux. This is another case where we have a jet, and this jet is flowing from left to right on your screen, and it's going unstable, and then the eddies are growing very slowly, and the peak in the eddy kinetic energy is out here, but actually most of the southward flux happens before then. And so why does that happen? There's all this eddy growth here, but all the southwards flux is just in this tiny little first meander. And the reason is actually because it's this first meander where there's baroclinic instability, which is shown by the blue line, and all this black line stuff, which is adding to EKE, is due to barotropic instability. And barotropic instability does absolutely nothing for the southwards flux along an isopycnal. So I've shown this from, 5 minutes, thank you. I've shown this from Alice's work, but Claire Jung's honours thesis did a much more comprehensive job of this, and her poster is out in the foyer, so you should definitely have a look at that. And she'll explain it much better than I am capable of. So I just want to quickly dwell on something which I think is important, which is that there's a really, really close connection, an unavoidable dynamical connection between this vertical momentum flux I've talked about and the along isopycnal thickness flux. And to understand this, all you need to do is take the zonal momentum equation in density coordinates. And if we take this for a particular layer, we're going to take layer K. And again, this is a transect across the Antarctic circumpolar current. So the isopycnals in purple are sloping up towards the surface. And if we just take this layer, which has an outcrop, so it experiences some input of momentum from the wind, it has a zonal transport. Think of this as the ACC coming out of the page towards you. And it has, this layer has a certain thickness, HK, and velocities and interface heights. Then if you distill down the zonal momentum equation, you can find that the time rate of change of the zonal transport, okay, that's what this is on the left, after you've done lots of averaging, has a correspondence with the meridional flux, okay? So think of this as the overturning. This is the residual flux up towards the surface. It has an effect on it experiences the wind stress, but only in a very small section where it outcrops. But all along these two upper surfaces, upper and lower surfaces, there's these two other terms. And these are the form stresses. And so what you're seeing here is a balance between all the stresses on each edge of this isopycnal layer, most of which is dominated by the form stress above and the form stress at the bottom of the layer. And that's all balanced at steady state. If the zonal transport is steady, that's all balanced with the Coriolis effect of this residual overturning. And so what that means is that there is a really tight connection between the residual overturning circulation and the zonal momentum balance acting through form stress, okay? I could talk about that one all day, but I recommend Emma Howard's paper if you're really interested in that. Okay, so just to spend 2 more minutes on what's happening in the Southern Ocean. We often characterise Southern Ocean eddies from the Eddy Kinetic Energy, and what I'm showing here is Eddy Kinetic Energy over 3 regions, estimated from satellite altimetry. And there's a couple of takeaways from this. This is a relatively old paper. We've redone it recently with Josue Martinez Moreno's work, but one point is that the Eddy Kinetic Energy appears to be increasing in the Southern Ocean, which is consistent with the increase in the southern annular mode and wind stresses over the Southern Ocean. The second is that there's a lot of interannual variability, and that this interannual variability has some relationship to the wind, which is difficult to unpick. More recent work looking at this trend tries to distill this trend down to more local regions and really argues that there's not very many regions where there's a strong trend in Eddy Kinetic Energy, and really calls into question these large-scale trends and what's producing them. And I guess I just want to highlight that the strength of the eddy field, the Eddy Kinetic Energy, is a product of a really chaotic, messy, turbulent process. The generation of eddies is important. The dissipation is also important. And something we've found more recently is that when we simulate this in an ensemble framework, this is a set of 50 eddy permitting ocean models. When we simulate the Eddy Kinetic Energy with this ensemble framework, what we find is we still find some interannual variability, which is forced by the forcing. But these grey individual ensemble members show that there's a really huge spread. And in fact, you could argue that the eddy field is dominated by this intrinsic variance. It's about, we estimate the intrinsic variability to be about 82%, even averaged over the whole Southern Ocean. And that makes it really hard to infer anything from recent measurements of the satellite estimated eddy kinetic energy in the real world, where we've only got one implementation. We've only got one observation. Okay. I could talk more about this one as well, but I'm not going to. Instead, I think I'm probably out of time, so I'm just going to leave these conclusions up and happy to answer any questions. Thank you.